In this tutorial, we will be discussing reaction rates and concentration. One can gain information about the rate of a reaction by seeing how the rate changes with the changes in concentration. So if we look at experiments 1 and 2, the NO2 minus, the nitrate ion, stays the same, but the ammonium ion doubles. Yet the overall rate for the initial rate of the reaction doubles. Similarly, if we look at nitrite in the experiments 5 and 6, it doubles here, and once again the rate doubles. This means that the rate is proportional to both ammonium and nitrite. When we write this as an equation, it comes out looking like this, where K is the rate constant, which is different for every single chemical reaction, multiplied by the concentration of ammonium and the concentration of nitrite. Remember that the boxes mean concentration. This is called the rate law. A rate law shows the relationship between the reaction rate and the concentration of the reactants. Note that we're always talking about the reactants here, to the left side of the equation. The exponents tell the order of the reaction with respect to each reactant. Since the rate law is KNH4 plus NO2 minus, notice that there's no number written in here or here. You know from previous algebra classes that if there's no number written as the exponent, it's automatically a 1. This is telling us that NH4 is the first order and NO2 minus also is the first order. The overall reaction order can be found by adding the exponents of the reactants in the rate law. So if this is a 1 and this is a 1, add this together and we get a second order reaction overall. Let's look at the reaction orders a little bit more closely. Let's take a generic chemical equation of A plus B yields C. Remember, we're looking at the concentrations of just the reactants. So the rate law is the rate is equal to K, which is the reaction constant, times the concentration of A to the N power, concentration of B to the M power. Notice that little a and little b are not written there anywhere. Do not make that mistake. Rate orders must be determined experimentally. Reaction rate orders are not found in the balanced chemical reaction. The exponents N and M are referred to as the reaction order. The reaction order values can be 0, 1, 2, or even fractions. The sum of the exponents of the reactants is called the order of the reaction. For example, if we have this as the rate law, where A is to the second power and B is to the third power, the overall reaction is fifth order. We're only going to look at the 0, first, and second order in great detail. In 0 order, the rate of the reaction is independent of the reactant's concentration. So if we look at this graph here, this is the 0 order. As the concentration decreases, the rate does not change at all. Over time, the reactant's concentration decreases linearly. So that gives us the rate is equal to K times A to the 0 power. Anything to the 0 power automatically becomes 1, so the rate is equal to just K. We can draw this as a graph by plotting A versus time. And the slope of that graph will give us the rate constant. The first order, the rate of the reaction is directly proportional to the reactant's concentration. So that's this red line. Notice as the concentration decreases, the rate also decreases. Over time, the reactant's concentration slowly decreases. So this rate is K times the concentration of A to the first power, which gives us rate is equal to Ka. If we drew this as a graph to try to find the slope, we'd have to take the natural log of A to get a straight line. In the second order reaction, that's the blue line here, as the concentration decreases, the rate decreases even quicker. The rate of the reaction is proportional to the reactant's concentration once again. So now we have Ka to the second power. In order to get a straight line for this, we would have to do 1 over the concentration of A. I mentioned earlier that in order to do this, you have to do it experimentally. You can't just look at the chemical reaction. So when comparing the reactant concentrations and corresponding rates between two sets of the data, if a doubling of the reactant's concentration, so remember the very first example we had, where the reaction rate, where the concentration doubled, the reaction rate doubled. That's the two things we're looking at here. If there is no change when that concentration doubles, it's said to be 0 order. If the reaction rate doubles, it's said to be first order, and if it quadruples, it's said to be the second order. So let's take a look at this. Derive the rate law and the units for K. Here we only have one reactant, so we only have one thing to look at. This doubled, 0.1 to 0.2. From experiment 1 to experiment 2 here, it quadrupled. So that means, if we look back at these rules up here, if it quadruples, it's the second order. Now to get the whole rate law, we also have a K here. It didn't ask for the K, although we could derive it. So rate is 0.020 is equal to the K times the concentration, 0.1, to the second power. That comes out to be 0.01. So that means our K is equal to 2. Now let's take a look at the units. I left the units out on this, just so that way we can look at the numbers themselves. But the units are moles per liter, and that means they're going to be squared. So that means mole squared over liter squared. If the rate is always going to be moles per liter per second, that means we need a moles per liter at the end. So that means K would then have to be liters per mole per second. That sounds confusing. We're going to go over that again. So if we have liters per mole times seconds, and we have mole squared over liter squared over here, one of the liters cancel out, one of the moles cancel out, and we're still left over with moles per liter. Let's take another look at that. The rate units is always a concentration or amount per time. For instance, molarity per second. To determine K units, you need to know the overall reaction order before doing so. The overall reaction order is 5 in this case. 2 and 3 is 5. To determine the units of K, we know that the rate is moles per liter per second. We know that we're going to take moles per liter and take it to the 5th power. So that means moles to the 5th, liters to the 5th. K units have to be such that both sides of the rate law will have the same units. The unit of K for this rate law would be liters to the 4th per moles to the fourth times seconds. Once again, 4 of those liters cancel out. 4 of those moles cancel out. So we still have moles per liter per second, just like we do on the left-hand side. Therefore, the units is liters to the fourth over moles to the fourth per second. Alright, so let's take a little bit more complicated one. From the experimental data, derive the rate law and the value in units of K. Alright, so we have 2 things here that are reactants, Cl2 and CH3Cl. Take it one step at a time. We know that the rate will eventually be rate is equal to K Cl2 to the N power and CH3Cl to the M power. But we need to figure out what all these numbers are. We do this by comparing. Rate we're going to use for the first one, let's get rid of this one first. Experiments 2 and 1. So rate 2 over rate 1 is equal to the K Cl2 N CH3Cl M over K Cl2 CH3Cl. If we use experiments 1 and 2, the Cl2s end up canceling out, and all we have are the CH3Cls. So rate of 2 is 0.029. The rate of 1 is 0.014. We have K. Cl for rate 2 is 0.05. For CH3Cl, 0.1. On the bottom we have K. Cl2 is once again 0.05. And then CH3Cl is 0.05. Notice that the Cl2s and the Ks can cancel out. That's then going to come out to be 2.07 is equal to 2 to the M power. To get the M down here, we have to take the log of both sides. And that drops that M down. That's just a mathematical relationship. So that comes out to be 0.301 times M times 0.301. Divide both sides. So M is equal to 1. So that means that this here is to the first power. So as of now, we have the rate is equal to K times the Cl2 to the N CH3Cl to the first power. Now let's try to find the N. We want to get one where CH3Cl cancel out and there's a change in Cl2. So we're going to do rate 3 over rate 2. If you flip-flop these, the answer should still come out to be the same. It's not going to hurt anything. Just make sure you're consistent. Now I'm looking at experiment 2. Cancels. The K cancels. Rate 3, I never wrote that down, is 0.041. Rate 2 is 0.029. Alright, so when we divide that out, we have 1.41 is equal to 2 to the n power. Which means we're going to want to take the log of that again. Which comes out to be 0.149 is equal to 0.301 n. N is equal to approximately 1/2, 0.5. Remember before I said that the exponents can be fractions. So that means at this point we have rate is equal to KCl2 to the 1/2 CH3Cl to the 1. Now we need to determine what the K is. So we can just pick any random experiment. I'm going to just simply take the first one. Let's rewrite our rate equation. So the rate here is 0.014 is equal to K 0.05 to the 1/2 0.050 to the 1. So that means 0.014 is equal to K times 0.224 times 0.050. Multiply that out and then divide, and we get K is equal to 1.25. But what are the units? We need to determine that. Well, we have to look at what's going on in the actual equation. So the rate eventually, we want it in moles per liter per second. That's our goal. So that means we have to have some units of K to equal moles per liter, that's to the 1/2, and moles per liter to the first power. So that means that's going to be moles 1 1/2, liters 1 1/2. And it has to come out to be moles per liter per second. Well, I need to get rid of one of these halves, so liters per half. I need to get rid of one of these halves, and I need seconds in there. So that means K is equal to 1.25 liters to the 1/2 per mole 1/2 second. And that's how you do the rate law.